Hi everyone, hope you're doing great. I am here to make a video summarizing some of the stuff we've learned this week about PES. I actually made this video already a couple times last night, and I finally finished at 3 with both videos, and then went to post it, and this one didn't work. So I'm trying to make it again. Hopefully it'll work this time. But I'm so glad to have you guys, and this will just go over. You can see I've put in some terms and stuff that when I was doing the PES homework, I thought maybe would be helpful, like things that came out to me as like maybe you guys would have questions about. If you have any other questions, then of course reach out to me and we can figure it out. We can have a Zoom session, just like a drop-in one, or whatever we need to do. I did want to let you know that I posted the key to all of the PES packets, both of them, under class docs, unit 8, everything else, PES, and then it's called key. So you can definitely feel free to check that out. Okay, cool. Well, let's just go ahead and get started. Maybe plus side, third time's the charm. Maybe it'll be like a faster, more efficient video. So the first thing I wanted to talk about was binding energy versus ionization energy. So those are two terms that were being used, and I want to make sure that we are clear on them. So binding energy is the energy of attraction between the nucleus of an atom or ion, which is its protons, and the electrons. So remember, the nucleus also has neutrons in it, but the neutrons have no charge, so they're not really involved in drawing in the electrons. The protons, however, have that positive charge, and the electrons have that negative charge, and so the protons are what draws in the electrons. The energy of attraction between the protons and the electrons is what we call the binding energy. Since the protons are pulling in the electrons, they're essentially binding the electrons to that atom. The stronger they're bound, the higher the binding energy. The looser they're bound, the lower the the binding energy. Now, the ionization energy is directly related to binding energy. So if binding energy is high, ionization energy is high. If binding energy is low, ionization energy is low. The only difference there is the definition. So by definition, the ionization energy is the energy required to remove an electron from an atom. So if an electron is bound really tightly to an atom, then it will also take a lot of energy to remove that electron. And typically, the electrons that are being removed are valence or outer electrons, but I talk about that a little bit in the second video, which thank God did work yesterday. Okay, so that's binding energy and ionization energy. Now, the next thing here is effective nuclear charge, and that came up a bunch of times. So effective nuclear charge is a combination of two things. A, the number of protons pulling in the electrons, and that's going to be really the key feature. Most questions about effective nuclear charge is really about the number of protons, But then there's also, and we learned this during the last Zoom, the electron repulsions, which cancel out some of that proton pull. And so to illustrate that, I can show you one of the questions that we were looking at from the packet. But essentially, the more protons there are in any atom or ion, the more tightly bound the electrons of that atom or ion are going to be, because there are more plus charges in the nucleus to pull everything in. But when we get to an outer level, like the outermost or the last energy level or the last subshell, the number of electrons will start to matter. The more electrons there are, the more those electrons repel each other, and that means they're being pushed away or out of the atom, so reducing the bonding energy a little bit more. So let's go ahead and take a look at the worksheet here. This was the worksheet, and this was the problem that we were looking at. So you can see here, this is the PES spectra for phosphorus. Remember that phosphorus, if I look at the periodic table, has 15 protons and 15 electrons. Sulfur has 16 protons and 16 electrons. And so if we take a look here, we can see that this is like 1s2, 2s2, 2p6, 3s2, 3p3. And this one's going to be 3p4. And that's just based on the electron configuration and the peaks that we're seeing. You can see that all of the peaks for the core electrons, the inside electrons, are are like the same intensity, but at a different space in terms of binding energy. So you can see the sulfur 1s has a binding energy of 239, but the phosphorus has a binding energy of only 208, right? And then 18.7 versus 22.7, 13.5 versus 16.5. So, and so forth. So basically, sulfur's binding energies are all more, and that can be directly attributed to the number of protons. So because sulfur has 16 protons, sulfur is binding its electrons more tightly to it, therefore has a higher binding energy. Because phosphorus has only 15 protons, it can't bind its electrons as tightly, therefore all of its binding energies are a little bit lower. However, when we look at the very last subshell, which is the 3p subshell right here, we see that unexpectedly sulfur actually has a lower binding energy than phosphorus. And this is going to be something specific to the 3p level, where we see like 1s both had 2, 2s both had 2, 2p both had 6, etc. But in the 3p level, sulfur has 4 electrons and phosphorus only has 3 electrons. So that means in sulfur, because there are 4 electrons, on that 3p level, there's actually more electron-electron repulsion, which is causing the electrons to push away from the atom, thus decreasing its energy levels, its binding energy. Hold on one second. I just have to check these texts and make sure it's not. Oh, perfect. Okay, so we can keep going. So that's the electron-electron repulsion. And because of that, of course, then the answer ends up being A here. So effective nuclear charge is about both. Boom. I am here. Got it. Okay, effective nuclear charge is about both the number of protons, okay, as well as this electron repulsion. I don't know why I wrote number 6, number of protons. But I would say majority of questions are going to be able to be answered based on the number of protons. So most of the time when I see the word effective nuclear charge, I just think that that is about the number of protons. Now, the next thing that comes up is electron shielding. Okay, and electron shielding is going to be important when we are comparing atoms or ions with different energy levels. Normally, when we use effective nuclear charge, we're comparing atoms or ions with the same number of energy levels. So, for example, if I have something with 2 energy levels and this one looks like that, and this one looks like this, this is a time we're going to compare effective nuclear charge, because we have equal numbers of energy levels, and a difference is going to be the number of protons inside. But when we're comparing things with outer energy levels, or with more energy levels, that's when electron shielding is coming. So let's compare this atom right here to this atom. Come in, sweetheart. Yes?
Undo.
Yeah, can I do it after I finish this video, please? I'm making this video. I'm going to do it later. Okay, thank you. Okay, so electron shielding is going to be about how the core electrons shield the outer electrons. And so you can see right here, this 2 energy level atom has these 2 core electrons and this 1 valence electron. But this guy right here has so many core electrons. Let's say it has a total of 10 core electrons and then this valence electron. So this valence electron out here could potentially be shielded from the nucleus because these inner core electrons are spinning around, and let's say this electron is blocking this nucleus, then this outer valence electron doesn't actually feel anything or feels very much less bound to the nucleus. That's what the phenomenon of shielding is. Whereas here, this core electron, despite how I've drawn it, is less likely to be shielded by only these 2 core electrons. So this valence electron, is less likely to be shielded by these core electrons. That would make something like this have a lower binding energy and something like this have a higher binding energy. So electron shielding is only going to come into play when we're comparing atoms with different energy levels, whereas effective nuclear charge will normally be used for atoms that have the same number of energy levels. Okay, I think that's everything I covered in the first video, the first few times I made it. And then you will go ahead and watch the next video to try to never lose my videos again. I finally purchased the upgraded version. So actually from now on, I should not have to make my videos in small chunks. I think I can make them all at once, which is going to be awesome too. But anyway, I hope you have a great weekend and I hope you find these helpful, and I'll talk to you guys soon once I figure out how to turn off this video. Guys, I can't turn off my video.
Wait, did you turn it off?
No, it's still going, I think. I legit can't figure out how to turn it off. Maybe if I plug this in, it'll work.
Nope, still on. Can you untie this knot? And my body's still hot. Feel it. No, it's